finish the one you're on right now, and then push your crossword to the side, and have your notes available, because we're gonna orally go over some of these warm-up questions here, because we're gonna elaborate more in class, especially in application phases. Okay. So I'm gonna ask for you to be ready, because I'm gonna call on you. Just popcorning around the room. All right. So draw and label the pH scale. So Ryan, what's the pH scale itself? From what to what? 0 to 14. Everybody, where are the acids on the pH scale? The 0 region, right? Okay, and then if you want to draw this someplace in your notes, of course, that's why I said leave like some space, and you've got some maybe some examples you can add, or specific applications you should add. And if you don't have your notes with you, then you've got a lot to catch up on, and I'm basically not going through every single slide as you were in page 2 last night, so just keep up. So it goes from 0 to 14. What's in the middle, everybody? 7. Okay, so the acidic side of the pH scale is 0, so what must be the 14?
3.
The basic side, also known as alkaline. Alkaline is a term you should know, means basic. Like the alkaline earth metal group, which is which group? Group 2, they have basic qualities. So what's their pH? Closer to 14, so anything greater than 7. So they're basically, when you drop those alkaline earth metal groups in water, they make a basic pH, which would be hazardous. Just like acids are really caustic and hazardous, and we wouldn't want to have exposure to like extremely acidic conditions, we also wouldn't want to have exposure to really basic conditions. They're just as caustic or just as harmful. So it goes A to B. It's pretty easy to see that. A to B. What's in the middle? Generally, it's called neutral. Not everything is. So you can still be neutral but not be pH 7, because if you're close to 7, you're still in the neutral range, like kind of like 6.5 to 7.5 is still neutral. Okay, describe how the concentration of hydronium ion changes from left to right. Everybody, what's hydronium's ion formula? Come on, loud and proud. H3O plus. Okay, so we have to know that it's H3O plus, and that's the term called hydronium. But many times we actually just call hydronium out as simply hydrogen, as in H plus, because if you notice, if I take one of the H pluses off of H3O plus, what does it become? Say again? Water. It's just water. So water itself is generally neutral. So water is like a carrier for an H plus ion. So if I have water and I add an H plus ion, it becomes hydronium. And so that's actually how we find them in solution, because water is the solution and the little H just piggybacks on top of it. So that's truly what we see, but we're lazy. We don't always want to write hydronium out all the time. So a lot of times we just write H plus, and we understand that these are interchangeable. Okay, so understand, if I say proton, that's the other word. If I say proton, if I say hydrogen ion, or if I say hydronium ion, they're all representing essentially the same thing, okay? Tomato, 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 okay? Why would I call an H plus just a proton? So let's backtrack to subatomic particles. What does hydrogen have? Like, what's it consisting of? One what? So we got hydrogen in the nucleus. It's got one proton. What else? One electron, right? Because it's got a mass of 1, right? So the mass can't consist of any neutrons, because the only mass of 1 is representing that single proton in the nucleus. It has 1 electron because that's what hydrogen has to make a neutral atom. 1 plus and 1 minus makes 0. So when I'm making an H plus ion, a cation, what have I done? What have I done to it? What have I taken out the only electron it had, right? So when you're an H plus, you actually take away the only electron you had, so what is left? Simply a what? A proton. So instead of saying hydrogen ion all the time, sometimes we just say proton, because it's literally the only thing left in the atom. So that's another name for a hydrogen ion. Again, these 3 things mean the same thing. Okay, write out 3 pH calculation formulas. I want you to say those 3 out in your group. Go. At least one from each person if you can. All right, we will use those here in about half an hour, okay? what does the term strong mean versus the term weak? So the term strong, Ryan's table, so actually, hold on, I'll go back. Elizabeth's table, back to you guys. What does the word strong mean in terms of acids and bases?
It's not a measure. It's strong acids ionize.
Perfect. Okay, so that means they ionize 100%. Okay, the word strong means ionizes 100%, and that's very important to us, especially with pH calculation. So everybody should be able to just contrast that. What does weak mean? It doesn't ionize 100%. That's literally the main difference there. 6 strong acids and 8 strong bases. Give me one, CJ, one strong acid. Okay, so 6 strong acids. SA means strong acids, okay? Hydrochloric, can you give me the formula for that? HCl. So we're practicing nomenclature and the formulas again. Hydrochloric acid. Ariane, another. You guys be ready. Nitric acid. Spell that or give me the formula for that. Kern, you're next. Cole, you're next. Good, HNO3. Nitric acid is HNO3. Kern? HBr, tell me the name of that. I'll come right back to you. Cole? Sulfuric acid, give me the formula for that. H2SO4. You guys are practicing nomenclature. Hydrobromic, right. Hydrochloric, hydrobromic. Those are some binary ones so far. Chandler, and then Jacob. I need 2 more. Iodic, right. So give me the formula. Very good. Okay, so hydroiodic. So we have this one that's binary. What's binary mean again? Just 2 elements involved. They're still crisscrossing charges, and it doesn't look like it, but they both have a 1 and a 1, a 1 and a 1, and a 1 and a 1, because those are the halogens. So these are the 3 binary. Okay, so we currently have only 2 ternary on the board, but Jacob's going to give us another one.
Hydrochloric acid.
Oh, we already got that one. Ternary, so it's got to be polyatomic involved.
It's HCl04.
HCl04, ready when you are. Give me a stab at it.
Chloric acid.
Perchloric. Okay, so this one, it looks like chlorate. ClO3 is chlorate, but that per means +1 oxygen, so it's perchloric acid. Okay, so how many are ternary up here? 3. So there's 3 binary and there's 3 ternary. And yes, you memorize those because what you should understand is when I say strong, Elizabeth, what does strong mean again? Good, so they ionize 100%. So what we would need to know is, like, if I were using HBr as an example, this is going to ionize. This is just like what we had on our, the I factors, the Van 't Hoff factors. We break it into the ions. So it makes H plus and Br minus 100% of the time. I'm elaborating some, and I don't know if you guys are getting sleepy on me. So do add some examples or some elaboration to your notes, okay? Yeah. Good. Walk that way, okay? All right, so the 8 strong bases, they make a little B. I tried to draw it on the periodic table. You guys saw in my notes. So it makes a B like this on the periodic table. Give me one of those, Aiden. And then Wesley.
Sodium hydroxide.
Okay, so sodium is our top one. So that is sodium hydroxide. I'm just going to put sodium there for now. Wesley, and then Anushka. I just need a metal that's serving as a base. It's right. You are looking at the slide. Potassium hydroxide, so it's right under sodium. Next, Anushka, and then Bryce. Lithium hydroxide, Bryce. Calcium hydroxide. I made my B really big. Let's fix that. Kendall. Who? Strontium. Yep. And Nana. Look at this slide that you should be looking at with strong bases. Ariel, you're next. Ariel, can you give me one? Guys, these are on your notes. There's no exception to you being able to answer those. Right in front of you. Just gonna wait on you guys. I'll just hold up the class. I'm ready. Nope, look on your strong base notes. It's right in front of you guys if you took extensive notes. Thank you. Donna, you have it right in front of you. Give me one. It's already on the board. Come on. Maverick. No. It's not on the list. Can somebody else give me the last one or two where we're looking at? Rubidium and cesium. All right. So we are moving on. It does look like a B if you kind of squint your eyes and turn your head. If you look 1, 2, 3, 4, 5, 6, 7, 8, there are 5 strong base with the hydroxides, of course, in group 1, and there are 3 in group 2. So you should have those 6 acids and those 8 bases memorized, because we will encounter examples, and you should know how to approach that example, especially knowing it's strong will help a lot. Everybody, what does the bracket mean? Whenever you saw a bracket, means what? I don't know if I actually specified this out loud on the notes. Bracket means molarity. Okay, so it means concentration. So if I ever put bracket, it means just looking for the concentration of that particular ion or acid or base or whatever we're talking about. Okay, so there are 3 definitions of acids and bases. Who defined the first one? Camilla? Definitions. There are 3 definitions of acids and bases. Who's the person's name that? Arrhenius, acids and bases. So they defined it very specifically. Hannah's right here. Riley, tell me the second person. Right, so we call him Bronsted or Bronsted-Lowry. If you ever see it's both names, it's just because 2 people helped us find that one. Bailey, last one? Lewis, right. So we have Arrhenius acids and bases definitions, Bronsted-Lowry acid bases definitions, and Lewis acid bases definitions. So there are 3 different definitions, but they all actually kind of relate to each other. But those definitions are going to be imperative in how we apply. And then let's jump down here. Monoprotic, diprotic, triprotic. Everybody, what do you think protic stands for? What's it kind of sound like? Proton. Okay. Remember, proton is another name for what? Hydrogen ion, right. So what do you think monodiene I refer to? 1, 2, 3. Give me an example of a monoprotic acid. An acid with 1 H in it. Hydrochloric acid. Give me an example of a diprotic acid. Sulfuric acid. And give me an example of a triprotic acid. Oh, technically hydronium truly is kind of acting as an acid, but I'll put it here, but it's not my best example. Well, get me started. It's gotta be what? What's got a 3 charge that would crisscross? Say again? Say again? Yeah, you can put a poly or not. Yeah, phosphate works for me. Okay, poly or a single would work. All right, so those are examples you should know so that you understand when I say monodiene tri, if some of them are H's. Okay, so we're going to talk, I'm going the wrong way. We're going to talk about that. We know how to do acids and bases. 2 properties, 2 for acids and 2 for bases. Name them out your group first. All right, so you should know your properties of acids and bases. Some of those are probably common sense because you've experienced lemons, and maybe you've said a not so great word at home and you got soap put in your mouth. I know who's ever had soap put in their mouth. Those are good parents, right? Those are good parents. Okay. So we have the two most common definitions that we utilize. the two most common definitions we utilize are Arrhenius and Bronsted-Lowry. The Bronsted-Lowry ones are what we're going to use extensively today. So I just want to remind you on how you can memorize this, because usually I say this in a video, but you guys just did notes on your own. So I'm going to start with Bronsted acids. Definitions off the cuff is what? 2 words. Proton donor, right? And so that makes the base the what? Proton acceptor. I like to say, this is my whatever 10th grade self, Bronsted acids are bad acids. Okay, so they're bad. Bronsted acids are donors. Bronsted acids are donors. And then the other one is bye-bye. Bronsted bases are acceptors. That one's not as cool, but this one's cool. Bronsted acids are bad acids. Okay. Yeah, you gotta be careful there. All right, so then Arrhenius, the other one, definition is what? Arrhenius talks about how acids behave in water. All right, so how behave in water. What is the what's the Spanish word for water? Agua. Arrhenius agua? Agua? Aqueous? I don't know. Just think A and A. Maybe that'll help you remember it. That's talking about how it behaves in water. So if this is the acid, right, it's saying HCO3 minus is the Arrhenius acid. What do we have to write for the equation? We have to write HCO1 minus plus H2O because it's specifically applying to water. Okay. And what does it say? Arrhenius said that all acids produce what in water? Okay, so what's hydronium? Okay, so what's happened here is that this H is the acidic hydrogen, and it's being donated. So it's kind of showing also whose definition? Bronsted, but it's specifically trying to indicate Arrhenius because it's saying, hey, I'm making hydronium in water. So this H gets donated to water to form H3O+. What's left? Well, remember, it's an H+. So it carries a charge away as well. So how does that modify it? CO3. So the CO3 has to remain, right? And then what happens to the 1 minus? Well, it's a 1 minus, right? We're already negative. We take away another positive. What happens? It gets even lower, right? So it's going to be a 2 minus. Well, who's this? Carbonate. So we actually should recognize most of the ions, specifically if you're good with your polys. Okay, so those are the two most common definitions, Bronsted and Arrhenius. Bronsted always just talking about donating or accepting, and then Arrhenius is talking about what's producing in water. Okay, we already did that, we already did that, we already did that mostly. Oh, what's Lewis specifically referencing in his definition? Lone pairs of electrons. So we probably remember Lewis was another, his name was utilized where? With dot structures, and those dots were representing what? The valence electron. So it kind of makes sense that he worked with electron spaces all his life, okay? So, and these examples are supposed to give you some indication as to which definition it's applying to. So what's this one here referring to? Which definition? Good, it's just donating. It's like here's a proton, it's passing back and forth. This one? Arrhenius, because it's look at the hydronium over here, H3O+. And then this bottom one is kind of showing what? Lewis, you see the lone pair of the dots, and they're being shared. Okay. Alrighty. I think we did those. We did those. What's hydroxide's formula? No, it's not. OH, right. So make sure you know hydroxide is OH minus, and we do crisscross charges when we form those bases. So if I was going to make strontium hydroxide, what's strontium's charge when it forms an ion? 2+. What's hydroxide's charge? Oh, I put ST. I always put ST. It's SR. SR 2+, and OH 1 minus. So what's the formula whenever you crisscross charges? Parentheses OH parentheses 2. Because if you put SrOH2 like this, you're not saying there's 2 hydroxides, you're saying there's 2 H's. That's not right. So do make sure you put your parentheses there. Okay, the weak definition is just the opposite of the strong definition. It's an incomplete ionization. So this was, I think, the last slide. No, not quite. But you did write this part down a little bit with your weak information. I did indicate in the notes that there was a difference. So what do you notice here in referencing the weak stuff?
It's reversible.
It's reversible, meaning that it's not 100% going to pull one direction and stay in that one direction. So it's not 100% going to make products. We will, I want you to name off maybe 2 or 3 weak acids, starting your groups first. So basically, there's only 6 strong acids. So anything else is going to be what? Weak. So come up with some weak ones first. Let's get 3 if we can get 3. Our new nearest table, give me a weak acid. Say the name in the formula if possible. Hold on, new nearest table. And then Estes table. Estes table, go ahead and start. You guys have to come right back to you.
Hydrocarbonic acid.
Whoa, hydro what?
Carbonic acid.
Not hydro. So remember, guys, when we say hydro, there's only one. So just carbonic. I got it, guys. I got it. He doesn't need any crap from you. So carbonic acid is, what's the formula for that?
H2CO3.
H2CO3. Good. So we don't say hydro because hydro is the term used for binary acids. This is a ternary. So he went with carbonic because carbonic came from carbonate. Okay, one from you guys?
Hydrofluoric acid.
Hydrofluoric, right. So HF, which is the one that's, if you look, chlorine, bromine, and iodine are all right next to each other. Those 3 are strong. Hydrofluoric is not strong. So we would consider that a weak acid. And then Kroll's table. Give me one more. You got a bunch of them to choose from.
Carbonic acid.
What? No. Noble gases are not going to do anything bonding-wise. Chem is tried. Very good, but let's get something else.
Sulfurous.
Good. So sulfuric. No, you're good. Sulfuric is a strong acid. So sulfurous acid is not formula. Come on. You can at least get me started. There's a common theme here. All acids start with what? Okay. Somebody else help me out here. No. H what? H2. Thank you. Okay. I do expect you to remember something from what we've learned with nomenclature. And it's been a little while, but we definitely have a lot of acids in this unit, so that's going to be our most common theme. Ooh, ah. Yeah. Is acetic acid a weak or strong? Weak. Write down the formula for acetic acids in place. And there's a picture model, but that's not terribly helpful. Write down the formula for acetic acid. CJ's table, get me started. Acetic acid. Somebody at CJ's table. All right, so you can get me started. It's an acid, guys. Hold up, it's an acid. H. Now. It's okay if you're wrong. Just get me started. C.
C2H3.
Good. So this was H plus, and this was acetate ion, and we crisscrossed, and everything was a 1, so we're good to go. So this is acetate, and we have to understand that there's only one H that's truly acidic, and it's the one that I wrote currently in the front. So this is a very important example. They like to trick you up a little bit on your final exam sometimes. They ask which is the acidic hydrogen or how many acidic hydrogens are present. It's just the H in the front that would be willing to pop off to form like hydronium, for example. Or there's an alternate way to write acetic acid, and it's CH3COOH. Okay? Count them up. How many C's? How many H's total? 4. How many O's total? This is acetic acid, but where is the acidic hydrogen? at the end, because what this actually looks like is CH3, C double bond O, OH. And these H's do not want to, they don't want to play. They want to stay with carbon and keep it happy with octet. And the only H that would be willing to be removed would be this one over here. And so this right here is the acidic hydrogen, which is the one that would be willing to pop off and join water and make an hydronium. So just don't want you to get tripped up on that if you ever come across that example. Thumbs up if I can move on. I don't know if you're writing things down, if you're just going to memorize all this, but just letting you have the time you need. What is this picture trying to indicate is happening as the HCl is popped in water? They what ionize? 100%. That's what it's trying to indicate to you. So sometimes you'll see pictures with that. What is this one trying to indicate to you? Partial. So there's one H that popped off of one, but these are still collectively together, so there's a partial ionization, meaning not complete, so not 100%. Okay, now conjugates. This was the big slide you guys wrote down, right? Conjugates are a little weird, and it's going to take some practice, so we're going to jump back into some lecture practice. This is near the crossword paper, so bring that back out. So one big deal that would be very, which helps makes a clear distinction between when we're talking about acids and bases and conjugate acids and conjugate bases, is the fact that conjugates are in the products. So the products are what we would look for if I'm looking and hunting for a conjugate. So that's pretty important. And so it's always the result of something deprotonating, or deprotonating just means to exchange an H+. So if I was ammonia, and this is ammonia, this is a weak base, or I'll just say it's a base, it doesn't really matter if it's weak or strong. It's a base. What is the job of a Bronsted base? It does what? It's an acceptor, right? So make this accept a proton. What should it look like now? Now it's not just an H that it's accepting, it's an H plus, right? Remember, it's accepting a full proton, H plus. So this becomes what? NH4. Well, does it have a charge currently? No charge currently, so when it gains a plus charge, it's just going to just show that 1 plus. So that is the conjugate acid of this base. Okay, so bases produce conjugate acids. So guess what acids do? Produce conjugate bases. So it's the opposite. So acids produce conjugate bases, and bases produce conjugate acids. So they're still a pair, because look how super similar they look. What's the only difference between those two? A hydrogen ion. Literally, that's it. That's the truest definition I can give you. It's a pair, the difference being one hydrogen ion. So whenever you label them, you tend to label them as pairs. So like you'll notice these arrows here are just indicating the pair of acids and bases. So this is who? What acid is that? Acetic acid, right? I heard somebody say it. That's acetic acid. And as I show you the pair over here, what happened to it? Right, there's one H plus difference between them. So in this case, I'm not going to say lost it. What's the definition of a Bronsted acid? Right, they donated an H plus. So that H popped off to make it overall a negative charge at the end. And then we'll look at some actual examples. So pull out the front page of the lecture notes right here. So I'm going to demonstrate two, maybe. Everybody's with me now? If you would halfway show the computer so I know that you're with me with the examples at this point, this is going to be where we pick up together. Alright, so we just did a similar one to this with acetic acid, but this one's written in the other form. So I want you to look at how we process this. I noticed that in the very beginning, I have to have something acting as an acid and something acting as a base. So I have to decide by looking at the products who did what. So if I track what's happening to acetic acid and I look at the products, which of these products looks like acetic acid? The second one, right? So that's the pair, because you notice they're very similar, just with an H plus difference. So what happened to acetic acid as it formed a product? Good, so it was a donor of an H plus. So that means this is labeled as the acid, because the acid is the donor. So who did it donate that H plus to? the water, right? There's only one other partner it could have donated the H plus 2, so if you are the acceptor, because you're going to be the complement taking care of the H plus, you are considered the what? The base. So we're going to talk about water being a base in just a second. So water had to have been the base because as this H plus was donated, water accepted it, and water made who? Hydronium. But we're going to call that its conjugate. Okay, so this is the base. Bases make conjugate acid. So this is water's conjugate acid. So then this acetic acid being the acid made a conjugate base. Okay? So all you're doing is labeling acid, base, conjugate base on these two examples here. See if you can pick up here in your groups. So you have to look into the future to see what's happening before you can make your decision. You do the rest of, there's 6 examples there, you can do the rest if you're ready. Thanks, Gordon. Just drop it right there. Drop it right there. Sorry, just. No, just leave it there. Just one. All right, check your work on the board. I tried to write down the logic with it. So in the HCl to Cl example, you notice that it dropped off an H plus, meaning it was a donor. Immediately noticing that, you would label that the acid, and its corresponding ion, the conjugate base. And since acids and bases have to play nicely together for that donation exception process to occur completely, the other one must have accepted, and you can tell that occurred because of the additional H it has at the end. So I'm hoping, I haven't made this clear, but I'm hoping it's obvious. Every single time you see an acid, what's probably on the front of it? An H, right? And every time you see a base, there's really not a rhyme or rhythm. You might see an OH, you might not. You might see the presence of no H, or you might, because we see an H here, like for example in ammonia. So if you see an H in the plus, an H in the front, it's probably the acid, but you do need to kind of double check, especially with behavior over the course of the rest of the reaction. Can I go past this? The next one? Okay, so if you've not approached the next one, I'm gonna ask for you guys to go ahead and tell me where these fall. So it may take maybe 30 more seconds there. Somebody at Ariane's table, can you guys tell me what you titled this one? Okay, so if you went from here to here, okay, so you labeled this one the acid, and this is its what? Okay, good. And why did you call this the acid? What happened? Right, so this was the donor. It donated one of its H pluses. Good. And then go ahead and complete that example for me. This would be the what? Base, and this would be its good conjugate acid. Okay. Kern's table. Pick up from here. Give me what you titled this one. Okay, so you went from here to here. You notice it dropped off an H plus, so it's a donor. Okay, so this is its what? Conjugate base. And then lastly, this would be the base, and this would be the conjugate acid. Good. And then, hang on, just got close. Not on the table, pick up from here. Okay, so that's the acid, and this is the base, and this is the good. Okay, so I'm hoping now you've also seen the fact that water can behave both ways. So if your computer is open, go ahead and shut it, because that's where you stay with me. Thank you. All right, so water can act both ways. It can act acidically and basically. What do you call somebody who can write with both hands? Okay, so that prefix in the front, what's the prefix in the front? Am, right? That basically means both. Okay, so what we should know is that water can be acid or base because it's amphoteric. That is the term you should know related to water. It is amphoteric. So what's the am in the front? Both. And then the phot kind of sounds like it's actually, I wish it said prot, but I was trying to make it sound like prot, but amphoteric means it can act acidically or basically, depending on the scenario it's put in. So it's very flexible, amphoteric. So they can surround the water. Both. Yeah, if you know language like science, it'll be good. All right, amphoteric, when we move past that term. Okay, keep staying. Give me a 1 out of 10. How do you feel on labeling conjugates? Like in a full reaction. Acid base, conjugate acid, conjugate base. Okay, thank you. Just wanted to see where we were. Yep, I'm gonna skip that one too. pH scale. Okay, look back over those pH equations right now, and specifically look for similarities. You maybe already noticed it, but look for similarities between the 6 equations you have. If you need to open back up your laptop, you probably can now. I want you to look for similarities. All right, give me something you're noticing. It's okay if it's not what I noticed, but it's what you noticed. Cole's table.
Two of them use negative log.
Okay, so we have a negative log aspect that's related to actually very similar equations. We have pH equals negative log of the hydronium, which hydronium is indicative of an acid or a base. Acid, right? If you ever see hydronium, it's trying to tell you something is acidic, or it's trying to see if you can tell like what pH is. So if you see H or hydronium like that, notice it's really honing on the acidic portion. But we notice that's very similar over here. So what is it measuring instead? Negative log of the hydroxide, which is now why they're, instead of calling it pH, they're calling it POH, which is the basic side of things. We memorize the pH scale because we understand, like, if it's low on the pH scale, it's acidic. If it's high on the pH scale, it's basic. But we don't memorize the POH scale. But what can you imagine? It's similar, but it's reversed, opposite. But why learn both of them if we understand that they have a relationship? The relationship between pH and POH is what? It's 14, right? They collectively determine together how acidic or how basic something is based on 14. 14 is the maximum technically of a pH scale. So while I'm saying that, you notice that, you know, there's always exceptions to rules basically all the time. Okay. So on your pH scale where you wrote down 0 to 14, write down exceptions. There are super acids and super bases, yes. And so there would be things that would exceed 14. And there could be things that would go below 0, meaning they would be what? Negative. So don't be scared when you see a negative pH, or don't be scared when you see a pH of 14.9. It does exist. It depends on how concentrated something is and how strong it is. being like it's a strong acid. So we will see those scenarios. Do not think they're wrong. You got that? Okay? So there's a couple of other things that you might find. We just see a lot of repeated hydronium hydroxides. It just depends on how you're manipulating it. So we're very interested in those ions and how those ions describe pH. Okie dokie? All right, let's take a quick breather. And, oh, it's not minimizing. We're gonna watch this guy for a second.
In this video, I'm going to talk about acids, bases, and pH. If you ask people what pH measures, they'll usually say if something is an acid or a base. And they might know that water has a pH of 7, that acids are generally lower than that, and bases higher than 7. But that's where a lot of people's understanding ends. And so I kind of want to explain to you what pH is and how it's determined. But before that, I want to tell you why it's important. I'm a biology teacher, and so everything kind of goes back to life. And so this is a protein. It's called myoglobin. It's found in your muscles, and it's going to be most active at a pH of 6. It's going to work at a pH of 5 all the way up to 7, but if we start to move our pH too low or too high, that protein is going to denature and our muscles aren't going to work. And so it's important that the pH levels remain relatively constant and they're not changing that much. But what is pH? Well, we've got to start by talking about water. And so this is a water molecule. Remember, we're going to have hydrogen here, 2 hydrogen atoms, and then 1 oxygen atom. Now, one thing that you need to understand is that this is a polar molecule. And what that means is there's a covalent bond between the hydrogen and the oxygen, and between this hydrogen and oxygen as well. And oxygen is really greedy when it comes to electrons. It's going to pull the electrons towards it. And so this is a sharing of electron between these atoms, but it's a polar covalent bond. And what that means is since oxygen's pulling the electrons towards it, it's going to have partial negative charge on this side of the oxygen, and the hydrogens are going to have a positive charge on the other side. And so if we were to add another molecule of water, these are not going to arrange this way. And in fact, what we'll have is that they'll be arranged like that. And so the hydrogen atom of one water molecule is going to be attracted to the oxygen of another. And that bond is called a hydrogen bond. A lot of students think that hydrogen bond is in here. No, that's covalent, but the hydrogen bond is going to be between the positive hydrogen, partially positive, and the negative oxygen. And that's why if we have one water molecule and the hydrogens are like positive and the oxygens are negative, and we have another one, they're going to line up like this. And as I pull one water molecule, the other one is going to go along with it. And that's why we have cohesion, and it explains a lot about water. But some weird thing happens with water. Sometimes that attraction is so great that this hydrogen atom will actually become detached from the water, and it'll become attached onto this other water molecule. That would be like me pulling this pinky off and attaching it over onto this other water molecule, leaving me just with this. And so what is that called? This is called hydronium. Hydronium is going to be H3O, and it's going to have a positive charge. What are we left with over here? This is a hydroxide ion. And so what is pH a measure of? Well, the P stands, we think, for the power of hydrogen. In other words,
when that H pops off, it's called autoionization. Okay, so when the water pulls in H plus off another water, it's called autoionization of water.
The amount of hydrogen. But it could also be the amount of hydronium or the amount of just free hydrogen ion inside the water. And so if we look at the power of that, or almost the percentage of that, that's going to be what pH measures. And in regular water, distilled water, the amount of this occurring is really, really rare. In other words, it's a 1 in 10 million chance that we're going to have hydronium. And this is really a molar.
Write down that value in scientific notation. 1 in, so 1 out of 10 million. So that would be like you doing 1 over 10 million. And I want you to write that down in scientific notation. All right, so what's 1 over 10 million? 1 times 10 to the say again? Negative 7. That is an important value. 1 times 10 to the negative 7 is the value, the concentration, put molarity on that. The the concentration of hydronium and separately hydroxide in water. Okay, so we need lights for me. I'm going to show this as a group real fast. What was the equation that brought together hydronium and hydroxide? Concentration. What is it? Hold on. What's the full equation? This is on your guys' paper. You have this written down. So OH negative times hydronium equals 1.00 times 10 to the negative 14, right? Okay, guys, how does this fit together? Where does this come into play? So the value for both of these ions, right? So if I plug 1 times 10 to the negative 7th in for each of those ions, what do I get? Okay, so this is a review of math. I am not a math teacher. What I do know you should know is that when you have exponents and you multiply them, what should you do? Add them. So it's negative 7 times negative 7. Negative 14. Boom. 1 times 10 to the negative 14. So this will always work. Now this, of course, is representing what pH of water?
7.
7, because we have equal amounts of the acidic ion, equal amounts of the basic ion. They should even themselves out to be neutral at pH 7. So what happens if I'm not going to have you calculate right now, but what happens if I say, okay, now I'm going to have 10 to the negative 6. These are all going to be representing hydroxide, okay? You guys with me? Okay. So did I go higher or lower than the negative 7? Was this a higher or lower concentration? Please remember, Logic. You're questioning yourselves. Okay, like that's a negative 7, that's 1 0 difference. That's a bigger number, right? So what's going to happen to this number? It's going to have to go lower, like 1 times 10 to the negative 8. So we just made it more basic and less acidic. It's still going to be 1 times 10 to the negative 14 because that's what it has to work out to. But what's our pH now? It's more basic, right? Can you give me a number? About 8. It actually is 8. Okay? This exponent system is just you know how it's log base 10 equals, log base 10x? That exponent is x. That exponent is representing what the pH is. So since we're talking about pH out loud, I know I could talk about pOH, but pH, this guy's concentration really is the important part. And so this concentration being base 10, I literally just take that exponent and say, yes, pH 8. But like I said, it's more basic because I made more of the hydroxide ions and less of the hydronium ions. So I can play with these numbers all day, but I want you to have some sense of what the numbers mean, not just plug in your calculator and go, it says it's 8. So I want you to realize that there's a balance here. So when it's 7, 7, what's the pH? 7. When you increase the hydroxide, you have to decrease the hydronium. What should happen to pH? They get more basicer, so it gets more basic. It has to go up. And if I increase the hydronium and decrease the hydroxide, what should happen? So more acidic, meaning less basic, meaning pH lower than 7. So there's a lot of ways we can state this, but I wanted you to see at least the particulate diagrams and understand how it's all related to just their relative comparison. All right, we'll come back to that if I need to. All right, let's do a couple of calculations. But here's the assumptions we make first. You should have written this down. We have assumptions because we like to make the math easy if we can. So if I have any of those 6 strong bases, I'm allowed to assume that whatever the concentration is of a strong base, or strong acid, that is the concentration of each of those ions. What are the ions produced from hydroboromic acid? Hydrogen ion and bromide ion, right? So if this is 2 molar, then this is 2 molar, and this is 2 molar. Which of these matter? For pH calculations, of course, hydrogen bromine is not going to give us any detail whatsoever. So this is the one I would use, and I would literally take that and plug it into any pH formula that has H plus in it. Okay, so I'm going to come right back to the second section. So I want you to find the pH of this particular solution. So what is the pH formula? pH equals what? Negative log of hydronium, right? And I told you, sometimes we're lazy and we don't want to write hydronium, so we just write H plus in its place. So that's the H plus concentration. Get stuff calculators. Get up now, get them. Or get yourself stretch break in, Estes. Specifically you since you're getting sleepy. Get up. Find the log function. Ooh, not log. You have a fancy calculator in my yard. That'll be easy. Alright, put in negative log of 2. Negative log of 2. What do we get? Woo! Can we have negative pHs, guys? Yes, and we're okay with that because sometimes the strong bases are very strong. Strong acids are very strong and concentrated. 2 molar is kind of concentrated. So pH is equal to negative 0.301. And there's no extra unit. There's nothing besides you saying equals pH. Okay, so we're only making that assumption for acids. Specifically for strong bases, we can do something very similar. We can say, oh, if I have a strong base, I immediately have the what concentration? It's not hydronium, it's hydroxide. So if I have 2 molar sodium hydroxide, what does sodium hydroxide ionize into? What and what? Sodium ion and hydroxide ion, right? So if I have 2 molar here, it means I have 2 molar of this guy and 2 molar of this guy. Which of these matters? Hydroxide, right? So I could then take this and plug this into what equation? Well, what would I be solving for? Good, POH, not pH, because that's not what hydroxide is going to immediately give us information about. So I would do POH is equal to negative log of hydroxide. So POH equals negative log of 2, which this is negative 0.301 again, right? Okay, but now, how do I make sense of that in terms of pH? Like, how would one transition from POH to pH? Which equation? You don't gotta look up here. It's right in front of you. Yeah, so I can now use pH plus POH. That equals what? 14. So since I know POH, I can solve for pH. So mathematically, what do I need to do? 14 minus that, right? So that's 14 minus POH. That's going to equal pH. So 14 minus negative 0.301 equals what?
14.
So again, you're like, oh gosh, we're above 14. Is it okay? Totally fine. And this is pH. So first off, you should be making some sense. Is this basic or acidic? Like super basic, right? So that sodium hydroxide that I provided you in this example, that 2 molar sodium hydroxide, that's going to be like measuring pH scale very, very basic. That's why I say it's pretty hazardous, because we have labs where we utilize this, and we want to be very careful because it could burn us. It's just like an acid could. Okay? So we've only used, what, 2 equations, really 3 equations so far? But there's 6, so I want to make sure you can practice with all of them. Most of the time to solve a series of questions related to pH, you only need like 2 or 3 at a time. There's no way I would ever have you use all 6 for one question. So you can be flexible in your mindset, okay? Can I move on? Okay. Oh, this is the only thing I did not tell you here. There's some weird issues with those di-basic bases, the ones with 2 hydroxides. And so here's the example. If I start you off with 4 molar barium hydroxide, it actually makes double hydroxides because of the 2 subscript. So instead of saying I have a 4 molar hydroxide solution, I actually double it because of the 2 on it. We don't do it any other time. There's only 3 instances, and it's for those 3 bases that have the 2. Who are they? Strong bases with a 2 on them. Barium hydroxide, who else? Say again? Strontium hydroxide and calcium hydroxide. This is the only time you ever double the concentration. Everything else is going to be the same. Okay, I want you to start with this data. I want you to solve for the 4 data points up there. You need to write down all the work, and I'll help you as well. And help you do your part. Use your pH formula that you can write in front of you. So you need to write down the given. You need to write down what's being provided to you. Like very clearly. So what does this equal? Oh, no, what ion is it describing? What's hydroxide? I know you can read it. Oh wait, sure. So I would be writing out to myself, concentration of OH minus is 6.4 times 10 to the negative fifth. I mean, you can read that really quickly and go, yeah, I know what hydroxide is, and then forget that you actually already know that part. So that's the molarity. And you really can go to anything from here. But let's just take it easy. Tamia's table, tell me where you guys want to go. Which other quantity do you want to solve for? Pick your poison, let's go. Well, no, what quantity? This one, this one, this one, or this one. All you have to work with is hydroxide. You can't go too crazy here. There's only 2 equations for that. Come on. Let's solve for POH, because that's probably the most logical one. Negative log of hydroxide is what we'll use. So then everybody's plugging or writing down the work so you understand the level of work I need to see. And then we're plugging in 6.4 times 10 to the negative fifth in parentheses, and let's solve. It should be 4.19. Okay, put a little box around that and put a box around the given because it's going to get messy here. All right, so we were provided with hydroxide. We said, let's take the easy route, plug it right into the hydroxide formula, which is POH. Cole's table, where do you guys want to go next? We got 2 quantities we can work with. We've got multiple methods we can use.
We could get pH using the pH plus POH equals 14.
Perfect, so that's one route. And anybody who's thinking something else, you're totally fine as well. You could proceed in probably 3 different ways here. So we have pH, we want to solve for, we have POH, we want to solve for pH. So pH is equal to, rearrange this for me. 14 minus POH, just making sure we're good on our math. I know you're like, that's subtraction, well, we can do this. Okay, so 14 minus 4.19 is 8. And this is pH. So you just notice how I'm labeling the identity. I'm not just saying, look back at the beginning of my work and lo, it's right here. I'm labeling it so I know what I'm talking about. Okay, talk in your groups how you want to get to that last one first. Last one, which is hydronium concentration. I'm going to show you that. That's why I wanted you to talk first. All right, come back to me. I'm going to show you both ways, okay? So I heard some people playing, and they were pointing at the board. They're like, oh, use that equation. Well, that's not bad. We can use that. I'm going to solve it this way and show you how to utilize anti-log on your calculator. So method 1, hydronium concentration times hydroxide concentration equals what? 1 times 10 to the negative 14. So I would then have to do what here to isolate hydronium? Well, how am I rearranging? You're dividing by hydroxide. Dividing by hydroxide, right? Okay, well, 1 times 10 to the negative 14 in parentheses. I'm telling you up front, people mess this up just because they just get lazy with the parentheses. That divided by parentheses, what was hydroxide? 6.7? Negative fifth. That was provided to you at the very beginning of this problem. So plug that in your calculator. parentheses, 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 all the way through and tell me what you get for hydronium. Sorry, louder and prouder for me. You got, look at your parentheses. I know from the exponent you're messed up someplace.
1.56
Negative 10. Double check and like verify right now you are good with parentheses because you'll get a bunch of questions wrong. That's a 10. And that's the molarity. 1.56 times 10 to the negative 10. Can I get a thumbs up? Yeah. Okay. Okay, so before we move from this question, I've started you off with a hydroxide, right? Immediately you went to what equation? I started you off with hydroxide concentration. You went to POH, and then you said, okay, got POH, now I can go to pH. And then I went from actually back from hydroxide, and I saw it for hydronium. So you could have done this at the very, very, very beginning, because the only thing we used was the very beginning data, correct? Okay, so the other route, which would be using pH, would be using the anti-log system. So doesn't yours say hydronium is equal to anti-log of pH, negative pH? So that's so log function has a base 10, correct? So the opposite of log is 10, because that's its base, raised to the power of whatever. So that's 10 caret negative pH. So if you need to write down that instead of anti-log, some calculators do have anti-log functions, others do not. So this is generally what I put in my calculator when I'm trying to solve for hydronium. So put in your calculator 10 caret negative, what was it? What was pH? 9.81. And you should get this. And tell me you do.
I got 1.54.
You're good. It's close. It's probably, if anything, just an exponential. So 1.5-ish, 5 times 10 to the negative 10 molarity, and that's the hydronium concentration. So tomato, you can use either one, but be familiar with both so that you can utilize it as needed. So before I move on, look at the ion concentrations and decide, is this substance acidic or basic? Look at the ion concentrations and decide if it's acidic or basic or neutral. Was it 6.4? Okay, I know some of you guys were like totally just looking at pH and you're like, it's definitely wet because the pH was 9, almost 10. But what you should be also willing to do is to say, okay, this number is wet compared to this number. This is smaller, so you have a smaller amount of wet. Smaller amount of hydronium, which is the acidic ion, and you have a greater amount of hydroxide, which is the basic ion. So you should be able to do both of those, not just looking at pH. All right, let's pause for a minute. Let's go to problem set 19. This is under. I have more to do. I think you're getting the hang of it, but I can always kind of get some more examples in like the next 5 minutes or so. Look at problem set 19, and you guys see the pH practice is towards. Problem set 19A. We are finishing problem set 19A tonight, okay? So go ahead and start on question 3. Start on question 3. Leave some space for, like, of course, those first few. But I'm going to let you get started now, and then I'll stop you whenever I want to do another example. Because I do have 1 or 2 more I definitely need to do with you up here. You are showing your work, because I will not be able to see any, like, calculator answers. I already provided the answers, so I was useless. your work on a 7-sheet paper to I'm not reading between those lines for a word. You have your equations right in front of you because you're eventually going to have to memorize them. You're still working on it to be expected. Let's get started, honey. Use an actual calculator because you wouldn't be able to use a computer. Thanks. And thank you so much for being like prepared to really absorb this information quickly in class. I think you did great. I don't know from that, but I think so. Finish the one you're on for a moment. I have 2 questions I specifically need to address to make sure you're good here. Finish the one you're on. Did you just get, what question you're on? 4 is the one with the, so yeah, I had like 3 people ask me about 4. 4 was the sulfuric acid one, right? Okay, you just take the ion concentration, or sorry, you take the acid concentration, and that is hydronium. That is H3O+. And then you plug it in pH. So negative log of 0.000287. I know it's dye, it's got the 2 H's, but we do not do anything special with any kind of acids. It's exactly what it is, okay? All right, come back to me in 10, 9, 8, 7, 6. I just want to make sure you can approach these correctly. 5, 4, eyes up here, 3, eyes up here, 2, 1. Okay, I need your attention for a good minute and a half. You ready? When you see a question like this, and it's asking for pH of sodium hydroxide, what do you recognize is provided to you? Andrew, you with me? What is provided to you? The molarity of hydroxide. So you should be recognizing that when you're provided with a base, it's immediately giving you hydroxide concentration. Can you go directly from hydroxide to pH?
No.
No. There's no equation with OH and pH. So we go from here to what? POH and then to pH. Okay, so that's, you would do a 2-step process to solve for that problem. Do not think that that is the H plus concentration. I just want to make sure you understand that that's how that's going to get you started. On the next one, write down calcium hydroxide's formula someplace. Work with me for a minute. I'd let you get started, but work with me for a minute. Write down calcium hydroxide's formula. All right, everybody, ready when you are. CaOH2 like this?
No, like
Parentheses, okay. So what's so special about this guy? It's the one that's a special one with the 2 on it, subscript, so it actually makes what? Double hydroxide. So if this is provided as 0.005 molar and it makes double hydroxides, What's the true concentration of hydroxide? 0.01 molar. So then that would be hydroxide's concentration. And that's how you would start, right? Not with that. That is no longer important. This is the only thing that's important. And then we could, how do we get to pH from here? POH and then pH. Okay, you guys know your equations at this point. Okay, keep working while you're working.
Oh, so there's 3 bases, yep. So there's 3 bases, only ones you ever double, which is the 3 bases in the one.
Basically, if you can get started, you're good to go. So you just need to interpret correctly at the beginning, and then you're good to go.